So now let's talk about some examples of real-world pipelines. So you saw this earlier in the course. In fact, you saw this in the first lecture. Here's ARM's big and little pipeline designs. And now you should have a better understanding for more of what's going on here. So the big pipeline has 24 stages and the little pipeline has 10 stages. You should be able to think about this and figure out something about what this means. So let's see how you're doing. Which one of these two designs is going to run at a faster clock frequency? Well, it's the big processor that's going to run at a faster clock frequency because there's a longer pipeline. That is, they took all of their work and they chopped it up into smaller pieces so they could run at a higher clock frequency. Which pipeline is going to waste more of its time on pipeline registers? Well, it's also the big processor. So it's running at a higher frequency and it's going to have less work in each pipeline stage because it has more. So it's going to have both more pipeline registers and they're going to be a higher percentage of the time. So you can look at it sort of graphically. Here's the little processor. It has long pipeline stages and not that many because it's running slowly, whereas the big processor has short pipeline stages and lots of them. So the big processor both has a larger percentage of its time on pipeline registers and a lot more pipeline registers. How about AMD? So here's a picture from AMD of their pipeline and how they think about it. Now this is kind of tricky to understand. Here's an easier to understand picture. So this shows what happens in all of the cycles, what's going on in each stage in the pipeline. This again is a little complicated, but let's compare it to our picture. So here's our simple 5-stage MIPS pipeline. Here's the instruction fetch for the AMD processor. You'll note they have 6 cycles of instruction fetch. That's a lot of time spent fetching the instruction. Here's their instruction decode. They've got 5 instructions for decoding the instruction and reading the register. Only got 1 instruction here for doing the execution. They've got 3 cycles for doing the memory, and then they've got the write back. So in a lot of ways this pipeline is similar to what we looked at, it's just stretched out a lot more because they want to run a lot faster. Most of the other stuff that you see in there is for the special idiosyncrasies of x86 for doing out-of-order execution and for floating point. So let's summarize what we've talked about pipelines. Pipelines allow us to run faster by increasing the clock frequency. That is, we chop our instruction up into smaller pieces so we can run faster, and by processing different parts of different instructions at the same time. That is, getting parallel execution out of the instructions. So we saw how ideally we'll get an n time speed up for an n-stage pipeline. But we saw there are some issues with pipelines. They don't work so well if the stages are unbalanced. And sometimes it's hard to chop operations up into the right size. We saw how we had to make the register file access in the processor take longer than it needed in order to balance the pipeline registers. If the pipeline is not kept full, well, we don't use all of the resources we have, and if we have empty whole instructions in the pipeline, it hurts a lot, and we'll see more about that later. And if there's too much overhead from the registers, this can be a real problem for performance. So we can't chop things up infinitely small because we'd spend all our time in pipeline registers. Today we talked about the MIPS pipeline and its 5 stages of instruction fetch, instruction decode, execute, memory access, and write back. And this is really important, so you should make sure you understand all of those stages. So here's a question. How many pipeline stages do modern processors have? Well, the answer is around 10 to 20. This is sort of a sweet spot for reducing the overhead of latches, optimizing the clock speed, and reducing the impact of branches. We're going to talk about the branch impact in the next lecture.